sorry, I used here T and U, should be T and U. What if instead of order, which is the smallest power of T and U that divide this polynomial, I use the degree, which is the highest power that appears in the polynomial, right? What are the properties that deg satisfy? So deg is also, I can send this to deg T of P and then U P. To fix ideas, let me do it just for one variable. And this is going to be necessary because I need to perform a change in notation for tomorrow's lecture. So imagine that you have Rx and you have the degree function which goes to Z or to the natural numbers, union infinity minus infinity. So so first let me take this away, take the 0.0 away, just to fix ideas. And if I have here a polynomial ai xi p, I send it to the max degree of p, is the max I, such that ai is equal to 0. So you agree that the degree of the polynomial 1 is 0, right? It has no, it's a constant polynomial.
Yes.
The degree of the product of two polynomials is what? The sum of the degrees of each one. What happens with the sum? Do you remember? So the degree is at most the maximal of the degrees. So this is almost a valuation, right? Because in my formalism for valuation, I should have this at least mean the P, the Q, right? So this is my formal definition that I gave yesterday and I report today. But I am finding a function which is almost the same thing, but the sign is reversed, and I am using max instead of min. So I should be able to call this a valuation too. So we agree that these are also valuations, but they are called absolute values. So this is just a math, and I will need this for later. So if instead of using, we use, this is called an additive valuation, and this is called multiplicative valuation, or absolute value. We will see later why. But do you agree that these are the same objects? Because what I can do here is to take the reverse order, and if I invert the order, then this mean becomes a mass. So what I'm trying to communicate here is that it doesn't, in valuation theory, it doesn't matter if you use the maximum convention or the minimum convention. With these signs, they define the same object. But psychologically, this is going to make an impact in our brain. So everything, I am trying to stress the fact that the brain is interesting because if you know something, I mean, for example, a toy that you had when you were a child. You feel comfortable with things that you know. And we don't feel comfortable with things that we don't know. Maybe we have fear, or maybe we lack confidence. And my point is that by performing, in tropical mathematics, by performing small changes in notation and small changes in definition, you can take one concept which is maybe not so natural for you. By making small transformations, you can take it to a concept that you see and you say, I know what this is. And your brain starts creating new ideas just by changing the shape of the things. So even if this looks stupid now, like, okay, you are just changing the notation and you are not doing great things, this is going to play a role, and then this is going to be important in the next lectures. Just save it for now that these are the same thing. And sometimes when we use the additive notation, it's for algebra, and if we use the multiplicative notation, it's for something else. But they are the same thing, just change of notation. Do you have any doubts? So, degree is a valuation, even if it obeys this rule rather than this. Now, let me go to the first theorem of today. I will try to give you a big theorem each day, so you keep being motivated. Valuation theory. And when I say valuation, some people put here proof. It may be or it may not be. It is the same. It's a very well understood branch of mathematics. In fact, I would say that it is a complete branch of mathematics, like linear algebra, from a theoretical point of view. Like, we know everything that we want to know about valuations. Valuation theory for fields is a very well understood subject. In mathematics. And there is a beautiful theorem for fields. So this is important. If your valuation, recall that a valuation is a triple. If this object is a ring and not a field, then there are still some things to do. Moreover, if this has zero divisors, so it is not an integral domain. But if this R is a field, this subject is pretty much finished. So there are books, and you can go to your library. There are excellent resources in which you can learn valuation theory completely, with no other questions, big questions in the subject. So the theorem that I want to share with you today is the following. This is like one of the jewels of the theory. let K be a field. I will explain each and every term here. So, this theorem says that there is certain equivalence relation that you can define on valuation, such that the equivalent classes of this relation on the set of all valuations for K fixed. So the first factor of this triple is fixed, and I'm varying the semi-field and I'm varying the valuation. But the first one is fixed, is in correspondence with some algebraic objects which are called the valuation rings of K. Do you know what is a valuation ring? Definition. R subset of K is a valuation ring if for every element, non-zero element, either the element lies in R or the inverse lies in R. I am sorry, the first hour of this lecture is still very algebraic, but I promise you that I will go to topology in the second round. Example. What are the valuation rings of Q? Then we can use a theorem from number theory, which is Ostrotsky theorem. Which says that a subring of Q is a valuation ring if and only if R is the localization of Z at a prime idea. So what is the localization? Are the quotients A divided by B such that P does not divide B. So this localization is A divided by B, AB in Q in Z, such that P does not divide B. Evidently, this is a subset of Q, right? Because I am taking quotients of integer numbers here. But I'm restricting B not to be divided by B. For example, which one is Z2? 2 is prime, right? So, are the rational numbers such that V is not paired. That's the localization of the integer numbers at the prime idea 2. And then if you put 3, then are all the quotients such that 3 does not divide the number that lies below. So Ostrowski theorem tells you that every valuation ring of Q is of this form. And if I use this theorem, then this theorem tells me which are all the valuations over Q. Of course, I have not shown you the theorem because it will take me so much time, and what I want to do in the course is to show you the beauty and the growth of the topical mathematics instead of focusing on specific results. I just want you to know how can you apply tropical mathematics in very different branches of mathematics. So, this theorem tells me that since I know all the valuation rings from Q, I should know all the equivalence classes of valuations in Q. And remember that a big family of valuations in Q are the p-adic valuations. So Ostrowski theorem and this theorem is characterized in the space of valuations in Q. So let me tell you that this is a number theory. This is a theorem from number theory. And this is a theorem from valuation theory. So here you feel the unity of mathematics, in which number theory helps valuation theory. Any doubt? Again, on one hand, I have to compute, I give you one field, Q. Compute all the valuation rings, all the rings that satisfy this thing. If you do this theorem tells you that you are characterizing essentially all the different valuations that you can construct over that field K. And as an example, I am showing you that for Q, this answer, we know this answer thanks to Ostrowski theorem, which is a theorem from number theory. And essentially, what you can put here is the set of p-adic valuations. Every valuation on Q is a p-adic valuation, or is equivalent to a p-adic valuation. This is what we are saying. Any doubt? So, in some sense, this is a moduli problem. In algebraic geometry, when you compute the set or the family of all objects that satisfy some property, you call it moduli or moduli. So we are computing the moduli of valuations of Q by computing the valuation rings of Q. And the theorem tells you that this is you can do this for any field, not just Q. For example, the real numbers or the complex numbers, or other fields which are more exotic. So this is the theorem. I won't discuss the equivalence relation because it is not interesting. It is boring. But just remember that there is an equivalence relation around there, such that you can factor the set of valuations and you get precisely the valuation rate. And the final comment around here is that valuations in some essence are algebraic because they are controlled by algebraic objects. So the definition that I gave you, in principle, that I erased it, but it was like a triple in some essence, the equivalence classes of these objects come from algebra because they are controlled. If R is a field, valuations my classical algebra. Because if I have evaluation over a field, I take its equivalence class, and this equivalence class is going to correspond to an algebraic object, which is evaluation rate. So this is why evaluation theory is very important, because in some sense, you're starting with algebra, you go to combinatorics, and then you come back to algebra. And in the meantime, all these different kind of interactions gives you new insights about the objects that are involved here. So evaluation theory is very beautiful. I just gave you a particular result, which is very important, but the theory is really, really nice. It's really, really beautiful. Now, have you studied some algebraic geometry? Please raise your hand if you have done so. Here. Okay, I will take some time to discuss some ideas of algebraic geometry, because I need them for my next part, which is the topology of algebraic varieties. Okay, so I will take 15 minutes or 20 minutes to introduce basics of algebraic geometry, and then we will go to the second application